Jairo Mendez Abreu. He's visiting us from University of St. Andrews in the UK. So just a bit about him. He did his PhD in the University of Padua, together with the Instituto Astrofísica de Canarias in Tenerife, Spain. And after that, he got another postdoctoral position at IAC. And after that, he moved to St. Andrews, from where he's visiting us now. And today, he's going to talk about galaxy bulges as tracer of galaxy formation. So, welcome, Jairo.
Bueno, la introducción solo en español. Solo dar las gracias por darme la oportunidad de dar esta charla y hablar un poco sobre mi línea de investigación. Y también decirles que, bueno, que si alguno al final de la charla pues tiene alguna duda o pregunta, la puede hacer también en español. No hay ningún problema, aunque la charla la voy a dar en inglés. So, the idea of this talk is to talk about a little bit about bulges. And I'm going to divide the talk into main parts. In the first one, I'm going to give you a bit of introduction about bulges and why we think they are important for galaxy evolution. And in the second part, I'm going to be a bit more technical, and I will show you some results that we have obtained using data from the CALIFA survey, trying to understand the formation of lenticular galaxies, in particular lenticular galaxies in the field, using a combination of photometric information. Here I show you some images from the SLOAN, where we have done some photometric decomposition to separate the different galaxy structures, and combining this photometric information with the stellar kinematics that we obtain from the CALIFA data cubes. So let's start from the beginning, and the beginning is always the definition. So what do we call bulges? So this seems like a very naive question, but actually there has been a long debate about what do we mean by bulges in the last, since the origin of the word. So historically, a bulge was defined as a central bright concentration of light with a few features of dust or star formation. Here I show you a photographic plate from a paper by Hubble in 26, where you can see this central bright prominence. And even if at this time the word bulge was still not in use, the word bulge was starting to be used in the 50s and the 60s, Hubble already figured out that there was some different component in the central part of the galaxies. Of course, our view of galaxies has evolved with time, and now we have much better images, much better techniques to study galaxies, and a kind of up-to-date definition for what a bulge is could be something like this. So a central bright structure, which is usually parameterized with a Sersic surface brightness distribution. A Sersic is just a parametric function which depends on 3 parameters. One is effective surface brightness, the second one is the effective radius, and the third one is what is called the Sersic index, which is just a measure of how concentrated the light is in the inner parts. And this central bright structure should be prevailing over other structures when we do morphological photometric decompositions. Here, this is just an example of an early-type galaxies where you can see this central bright structure in the center. And this is the surface brightness distribution in 1D. So the black dots represent the surface brightness distribution. And here, maybe you cannot see well, but there are 3 lines corresponding to the bulge, which is this dashed line. This is the disk, the dot line. And here we have also included a bar. So this inner component, defined in this way from photometric decomposition, is what we are going to call bulge throughout this talk. But what we are interested about bulges, why do we care about bulges? So there are many interesting things about them. I have just picked 3 different topics that are close to my research, just to show you the importance of bulges to understand galaxy evolution. And when you think about bulges, probably the first thing that came to your mind is the morphological classification, right? So already in the times by Hubble, galaxies were classified mainly depending on the ratio of the light coming from the bulge from the light coming from from the disk, for example. And this is the sequence that Hubble defined. This is the original drawing from Hubble, where you have elliptical galaxies in one side, so everything is an spheroid, everything is kind of a bulge. And then galaxies, we have the lenticular galaxies placed here in a kind of transition phase between the ellipticals and the spirals. And then the spirals are also classified depending on the bulge size with respect to the disk, right? Our view of galaxies again and our techniques to study galaxies has evolved a lot. And now we have much better images, and this is an up-to-date as well Hubble diagram, but still we are using this kind of morphological classification to understand galaxies. So even if we have these wonderful images, in this case, these are from the Spitzer telescope, they are from the SINGS team, still we are using the bulge and the bulge to total ratio, let's say in luminosity, to define the Hubble sequence. Another important thing about bulges is how do they contribute to the total stellar mass in a galaxy. This is a plot from a recent paper by Moffett and collaboration using the gamma collaboration, where, for example, in the lower panel, we can see the fraction of the total stellar mass, which is contained in bulges, which is this line over here, and in disk, which is this line over here, as a function of the total stellar mass of the galaxy. So you can see how for galaxies, let's say massive or massive than 10 to the 10 solar masses, the fraction of light coming from the bulge is quite significant. And if you integrate all this curve, what they got is that bulges contribute to 50% of the total stellar mass in galaxies. So if you want to understand what is happening on galaxy formation or in galaxy evolution, bulges are an important piece of the game. Finally, something that is now kind of a hot topic, and in every conference that you go about galaxy formation, you will hear about galaxy quenching. And I will talk a bit now about how bulge can be also related to the quenching of galaxies. So for those of you not familiar with the quenching, if you plot a large sample of galaxies in the color magnitude diagram, we have a bimodality. So we have that some galaxies are placed in a kind of a blue, what we call a blue cloud, while some other galaxies are placed in the red sequence. So the idea of how galaxies move from the blue cloud to the red sequence, if this is a quick process, or there is a kind of a slow process in the blue cloud and they move, or even if they go up and down, this kind of process is what we try to understand and is what we call galaxy quenching. So there are several evidences related to the influence of bulges in galaxy quenching. Here I show you two plots. In the left panel, this is a plot from a classical paper by Kaufman and collaborators in 2003. And in this plot, what they show is that in the y-axis, what you have is a proxy for the age of the stellar populations. And in the x-axis, what you have is a proxy for the concentration of light in the galaxy. So you have here two different blobs of galaxies. So all galaxies are associated with galaxies with higher concentrations, while when we look at the young galaxies, they have lower concentrations. So the concentration of light seems to be related with the age of the stellar population, with the aging of the stellar populations. This is a more recent plot by Black and collaborator in 2014. And here what you show is the fraction of passive galaxies, so the fraction of galaxies which are in the red sequence as a function of the total stellar mass. But in this time, the colors represent different masses of the bulges. So you can see how there is a logical trend for galaxies, for more passive galaxies being in massive galaxies. This is expected if you think on elliptical galaxies dominating the high mass n on the luminosity distribution. But the interesting thing here is that for galaxies with the same stellar mass, for example, 10 to the 10, there are more passive galaxies where the mass of the bulge is increasing. So the mass of the bulge is related to the fraction of galaxies in the red sequence. So the fraction of galaxies which are red and dead. So there are some evidences that seems to that the concentration or the galaxy mass or the bulge mass are related to the quenching of the galaxies, but it could be also not the whole story. For example, is the correlation that I show you now means that a causation as well. So for instance, if the correlations that we are seeing are really the cause of the quenching, then it's real that the bulge growth is what is stopping the star formation. And this can be, for example, because when you make the bulge bigger and bigger and massive, it can stabilize the disk somehow, and it can prevent the star formation. So this could be one answer to the question. But this is not the only answer, because there could be some indirect mechanism acting also in the same way. For example, we know that there is a correlation between the mass of the bulge and the mass of the supermassive black hole in the center of the galaxies, right? So if the bulge is growing, you need to feed the black hole to make the black hole bigger as well, and you can trigger AGN. And we know that AGN feedback is an efficient way to stop star formation. There could be also something similar with the halo. I mean, if we create this growth of mass in the bulge by mergers, for example, you are merging different galaxies, you are merging different also dark matter halos, and we know from simulations that when the dark matter halo reach a given mass, the gas which is floating in this dark matter halo, when it's infalling into the galaxy, gets shocked, gets heat, and then it cannot fall into the galaxy and be this fuel that we need to continue with the star formation. So the galaxies will fade and will become red as well. So this is a hot topic. So this is just to focus a bit on the importance of bulges in galaxy evolution. But what can we learn if we study bulges about galaxy formation actually, right? In the current paradigm of galaxy bulges, we divide bulges in two different kinds, right? There are what we call classical bulges, and there are what we call disk-like bulges, or pseudo-bulges. Maybe you have here also this word. And the separation of these two types of bulges has been mainly done from an observational point of view. So here, these are just two examples. So classical bulge is related basically to an elliptical galaxy in the center of a spiral. In this sense, the bulge that you see here should share some properties with elliptical galaxies, while you can see how different the center of the galaxies are when you look at the bulge, which is more disk-like. And by disk-like, I mean that we can see features that we see in disks, like spiral patterns, rings, or dust. So this is a quite, let's say, qualitative way of separating the two kinds of bulges, but with the time, we have done something better. And there are several observational features that can be helping us to separate the two different kinds of bulges. Let me go a bit over these different observational properties. For example, from the photometric point of view, there are some words saying that classical bulges are associated with high Cercic index, so higher concentration of light in the center of the galaxy. And disk-like bulges are associated with low Cercic index. This is a plot from a recent paper. This is a review paper in 2016, where these guys, Fisher and Drury, they classify bulges visually into what they call pseudo-bulges or disk-like and classical. And this is the frequency of these bulges as a function of the Cercic index. So you can see how most of the disk-like bulges are here in the region of low Cercic index, while for classical bulges, they are more concentrated in the center. Still, there is a lot of scatter, so it is not so clear if this division that they do between the two, depending on the Cercic index, is completely true or not. Yeah, the classification into disk-like or classical is visual. So they just look at the morphology by eye. And then they apply a photometric decomposition and compute the Cercic index with a bulge to this decomposition. Yes. Yeah, the Cercic index is the parametrization of the bulge, yes. There are also some hints for separation of the two different kind of bulges from the stellar kinematics. In this case, I show you here a plot by Fabricius et al. In 2012, where they show the ratio of the velocity, the rotational velocity over the velocity dispersion. In this case, in this panel here is for classical bulges. In this panel here is for pseudo bulges. And you can see how there is a different gradient within the bulge. This is the radius in bulge units. So there is a different gradient for classical bulges and from pseudo-bulges, implying that somehow classical bulges are more dispersion dominated, as you would expect for ellipticals, and these like bulges, as the words say, are more rotation dominated. Finally, also from the stellar populations, we can see some differences. This plot is maybe not so clear. This is also taken from this paper in 2016. What they show here is the star formation, the specific star formation rate as a function of this Sersic index, this central concentration of light, right? And you can see maybe a kind of relation in here. It's not so clear. But basically, this tells us that galaxies with bulges with low Sersic index has higher specific star formation rate, and the opposite for higher Sersic index. So if we assume that in here we have classical bulges and here we have disk-like bulges, there is a relation that there is more resonant star formation in disk-like bulges than in classical ones. So this is from the observational point of view, but we want to learn something about the formation of this system. We want to use this separation or use these properties to understand more about the formation of the galaxies. So what is interesting here is that there has been some theoretical models that has been worked out to explain the different properties of the different kind of bulges. For example, we can form classical bulges using major mergers. This is a plot by Hopkins and collaborators in 2009, where they show the bulge to total luminosity ratio, so the contribution of the bulge to the total light of the galaxy again, as a function of the total stellar mass. And in here, what is interesting is that in their simulations, where they don't include the gas in the simulation, what you have is this line over here, which is not reproducing the observations, which is this shaded line over here. However, when you include gas in a proper way, when you include gas in the mergers, what you get is this line over here, which is reproducing your data quite nicely. So dissipation is important for the formation of bulges, and it's important for the formation of these classical bulges as well. Another possibility is what is called now the kind of clamp merging or clamp coalescence. And this is based on the idea that a high redshift galaxy has a higher amount of gas, and the morphology of the star-forming galaxies is dominated by this giant kiloparsec size scale clamps of star formation that we can see here in these simulations by Bourneau and collaborators. And the idea is that these clamps, by dynamical friction, they will evolve, they will spiral into the center of the galaxy, they will merge, and they finally will form a bulge that will share the properties that we expect for classical bulges as well. So this is a new line for the formation also of these classical bulges. And finally, also minor mergers can have a contribution to the formation of classical bulges. These are also simulations from Eliche Moral in 2006. This is the Sersic index as a function of the bulge to disk in this case. If you look here at the inset, the original galaxies are these three over here. And when you start bombarding these galaxies with different, with minor mergers, what you get is also the galaxies that are in the mergers, they get disrupted, but the mass from these galaxies fall into the center and contribute to the growth of the bulge. And finally, what you get is an increase in the Sersic index and an increase in the bulge to total on the bulge to this ratio as well. So you move galaxies towards the direction of having classical bulges as well.
What do you mean by minor mergers?
Minor mergers are usually with a mass ratio of 1 to the 4. Yeah, larger than 1 to the 4, 1 to the 6, 1 to the 7. Okay. However, if you think on this, there are many ways of creating classical bulges, but to create this kind of disk-like bulges, there are not so many. And probably the main way that has been worked out to create these disk-like bulges is using bars. So it's using the changes in the galaxy potential that you get when you have a bar. When you get a bar, you get some instability, you get some torques happening into the galaxy potential. And there, you can have some inflow of gas from the outer part of the galaxy to the central parts of the galaxy. This is an image. These are simulations, and this is an image from H1 showing how really you can, how the bar can really get the gas flowing through the bar, getting into the center, creating a star formation, and producing what we call this like bulge. So these are several ways that we can create bulges. And we are going to use now these properties, and we are going to try to figure out what is the main formation mechanism using these ideas for the formation of our lenticular galaxies. So now I'm going to move to the second part of the talk, when I'm going to talk to you about the formation of lenticular galaxies and about the work that we have done with CALIFA. So to start again, what do we know about the formation of this particular kind of galaxies, right? So actually, we think that there are two main lines of thought for the formation of this system. Probably the most used one is that lenticular galaxies are the end product of a spiral galaxy. So you have a spiral galaxy in the field. When this spiral galaxy falls into a more dense environment, there are several mechanisms that can act. For example, ramp pressure stripping happening into clusters. So the gas is removed out from the galaxy. You stop a star formation, and the spiral galaxy, which is blue and start forming, gets red and gets more similar to what is a lenticular galaxy. Other evidences for this kind of mechanism acting is the morphology density relation. So we know for a long time now that if you look at the fraction of lenticular over spiral galaxies in the center of the cluster, this fraction is higher than when you move to the field. So there should be some mechanisms transforming spirals into lenticulars if we think on this morphology density relation. However, there are also some evidence that S0 live not only in clusters, but they live also in group-like environments or even in the field. So processes acting on the gas, stripping the gas out for galaxies, cannot be the reason why we have these S0s in the field. Also, this is a paper also using CALIFA data. There are some evidence that the angular momentum, when you define the plane angular momentum versus concentration for spiral galaxies, is not the same as the one that you get for lenticular galaxies. So it's not clear how you can transform a spiral galaxy into a lenticular galaxy without changing the angular momentum. So it's not clear how you can have this kind of lenticular galaxies from this. So mergers can be also a way to form these galaxies in the field. So the sample is the Khalifa Survey. I guess that most of you are very familiar with Khalifa. Sebastian is the PI, is working here. I'm sure that you know a lot of this. So I just put this slide as an introduction to the survey. Just remember that it's an integral field survey, so this is important for us. We want to isolate the central region of the galaxy. We want to extract information from the stellar kinematic from this region. So IFU data is important. Here are some plots representing just the Hubble type as a function of the number of galaxies that we have in the survey, and also as a function of the stellar mass. The final sample of Khalifa is 667 galaxies. The data is already out, so you can use it, and all the information is in this paper from this year. So an important thing that we have done with Khalifa is to parameterize the stellar components. So we have done this using photometric decomposition. This is in a paper that I did this year. It's already in the archive. And the idea is that we can use the photometric information from the SLOAN Digital Sky Survey images, to decompose the galaxy in different components. What we have used is my code that I developed here in 2008. Some people here also in the audience, we have used this code for other purposes, not only for Bulges. And we have decomposed all the CALIFA galaxies, but those which are really edge-on, because due to projection effects, it's very difficult to do the photometric decomposition, and also the interacting galaxies, because in photometric decomposition, you assume some kind of symmetry that you don't have when you have mergers. At the end, our sample is of 404 galaxies. We apply this two-dimensional analysis in these three bands of SLOAN. And another important thing is that it's multi-component. So we were very interested on the central part. So we were very interested on the shape, for for example, in the properties of the bulges. And if you really want to understand the properties of the bulges, you need to include a bar. So if you don't include the bar in the photometric decomposition, most of the light from the bar will go into what you will define as a bulge. And then your properties will be completely scattered. So the inclusion of the bar is important. And then we also include the different type of disk that we think that exists in galaxies. So type 1 is a completely exponential. The type 2 is this breaking profile when you have a downbending profile. And type 3 is when this break goes up and you have an upbending profile. Here is just an example of how the photometric decomposition works. So this is an image. This is an R-band image from Sloan. This is the model with the 3 components. We have included here a bulge, a bar, and a disk. These are the residuals. And the bottom panels are the one-dimensional representation of the feet. So here again, you have the one-dimensional surface brightness distribution and the 3 components that we have decomposed the light. So some results that we have obtained from these photometric decompositions. So this is one of them. Here I show you this is the fraction of galaxies that we have fit with a given combination of profiles as a function of the total stellar mass of the galaxy. And there are 3 main behaviors that are interesting in this plot. The first one is that at high masses, what we have is only galaxies that we have modeled either with a single Cercic, so this is what we will expect to be an elliptical galaxy, or with a bulge to this, but with a high bulge to total ratio. So bigger bulges or only spheroids are dominating this part of the luminosity distribution. When we go to intermediate masses, what we have is this line over here, which represent models with a bulge and a disk, but with a low bulge to total ratio. And by low, I mean less than 0.2. So this kind of galaxies dominate completely the intermediate mass range. And when we move to the very less massive galaxies, let's say, most of these galaxies do not contain a bulge. So this is a kind of similar figure as the one that I showed you in the introduction, where I show you the mass fraction of the bulge and the disk as a function of the stellar mass. So this is a kind of the same one, showing that big bulges dominate the high mass end, but when you move to the low mass end, you don't have bulges at all. And this is still a problem for cosmological models of numerical simulation, reproducing the high fraction of galaxies with small bulges that you have at low masses. Yeah, we can discuss about this. This is a kind of another way of showing the same thing. This is in this case, this is the bulge to total ratio as a function of the Hubble type and the total stellar mass. Here, the bars represent the observed distribution, and the stars represent the volume-corrected distribution. So using CALIFA, one of the good things about CALIFA is that you can correct in volume because you have a good selection definition of the sample. So you can see again this trend. So of course, lenticular galaxies has bigger bulges than late-type galaxies. But even if these are lenticular galaxies, look at the bulge to total fraction. It's about 0.3, 0.4. So even if you have these lenticular galaxies that you usually assume to have bigger bulges, the contribution to the light is about 0.4. It's about 40% of the light. So it's not too much. And this trend can be explained as this trend because you have also that later types are lower masses. So we have, again, this trend with the bulge to total luminosity as a function of the total stellar mass. But now let's go into the details about the sample, the lenticular sample that we have defined, and how we have used the stellar kinematics, right? We are using CALIFA, so we are using the spectroscopy from CALIFA. This is what we are interested in. The sample of lenticular galaxies that we have worked with comprise 25 galaxies, and it has a very particular sample selection. And this was not done in purpose at the beginning, but at the end, this is what we have. So I say that it's very particular in the sample selection because if you look at the stellar masses, this is the distribution of the stellar masses for the whole mother sample of the CALIFA galaxies. The black is the masses of our sample galaxies, of our lenticular galaxies. So they go from 10 to the 10 to 10 to the 11. So they are limited to this very narrow range on stellar masses. In red here is a subsample of elliptical galaxies that I have used for comparison, and I will show you some results later about this sample. So our lenticular sample is very particular in stellar mass, so from 10 to the 10 to 10 to the 11. In this plot, I show you the local density in terms of the nearest neighbor. Here, our galaxies are in the low density part of the distribution. So in here, you will have clusters. So none of our galaxies are in clusters. They are in low density environments. And if you look at the color magnitude diagram, they lie in the same part of the diagram as the elliptical galaxies. So they are very red galaxies as well. So these are related to the global properties of the galaxies, but keep this in mind because it will be important at the end of the talk. But what we want to do is to use this comparison of the photometry and the stellar kinematics to know something else about the formation of lenticulars. Here I show you just some maps of the stellar kinematics to give you an idea of the quality of the data. So here, 3 different columns are 3 different galaxies. The top row represents the intensity. So it's the data cube has been integrated over all the wavelength, and this is the integrated light from the data cube for the 3 different galaxies. The middle panel represents the velocity map. So in red are part of the galaxies that are going in the opposite direction to you, and in blue are part of the galaxies that are moving towards you. And the bottom panel represents the velocity dispersion map. So red parts represent part of the galaxy with higher velocity dispersion. And I have overplot here an ellipse, and this ellipse represents the extension, the one effective radius of our Bulges. It's the one effective ratio, the effective radio, the ellipticity and the position angle of our Bulges. So this represents the region of the galaxy where our Bulges dominate. And if you look, for example, at the velocity dispersion, they correspond quite well with the region where there is an increase in the velocity dispersion. So this is what you would expect if you have a concentrated light in the center, right? But this is very qualitative. So we need to quantify further how the stellar kinematic and the stellar dynamics of these Bulges is. Something that is used to understand the stellar dynamics of galaxies or of galaxies in general, yes, is now this diagram, the lambda epsilon diagram. For many times, we were using the V sigma versus epsilon diagram. This was defined by Bini and by many people in the 80s and in the 90s. Then the Saron team defined this new parameter, the lambda, which is defined in this way. And we are now moving to using more this diagram to understand the galaxy dynamics. And I'm going to explain you a bit more about this plot. So the lambda parameter is defined in this way. So here you have, this is the flux in each spaxer. Remember that we have a spatially resolved spectroscopy. So for every position in the galaxy, we have a spectra. And for every position in the galaxy, we can determine a flux, the radius, and the velocity of this point. And in here, we have, again, the flux and the radius. But in this case, we have the square root of the velocity and the velocity dispersion. So this is a kind of a specific angular momentum. In here, you have some kind of the angular momentum divided by the total potential of the galaxy. So this is the definition of lambda. And if you plot lambda as a function of the epsilon, which epsilon means the apparent ellipticity of your system, you have that this plot depends on 3 different variables. The first one is anisotropy, which is what I show here with this line. This line corresponds to systems with the same anisotropy. And when I mean anisotropy of the orbits, if you remember, the velocity dispersion tensor have 3 components. So you have the vertical, the z component, the tangential, and the radial component. If you assume that the radial and the tangential are similar, you can define beta, which is the vertical anisotropy, which is the relation between the velocity dispersion in the vertical axis with respect to the radial component. So this is the definition of the vertical anisotropy that I'm plotting here. So when you have beta equals 0, is that these 2 terms are the same. So you have the same vertical and radial anisotropy. Apart from this, what is implicit to this plot is the intrinsic shape of your system, which I plot here with these 3 axes. and the inclination of the system. So for example, if we pick from here one line of the same anisotropy, we can see how for different intrinsic shapes, this is 0.5, 0.6, so these are different flattenings of your ellipse in the intrinsic distribution of the system. Then this is for the edge on view, and when you move from the edge on view, where you have that your intrinsic ellipticity is equal to the apparent, then you will move in this way, and when you are moving your galaxy from the edge on view to the face on view, the final output of this is that you will have always zero ellipticity. This is because we are assuming oblate spheroids. This is important. So when you have your oblate spheroid, which is seen edge on, you are over this line, depending on how is your intrinsic ellipticity. And then when you are moving, you will get to a completely circular system, right? But you will be asking now where are our Bulges in this plot. So this is the answer. So this is again the angular momentum versus epsilon for the angular momentum measure within an aperture which correspond to our Bulges. So these are the black points. Here I have plotted again the line for the isotropy, so beta equals 0. And I have plotted here another line in which the anisotropy goes with this function of the intrinsic ellipticity. And these lines over here represent, again, the deviation with inclination from when you are in the edge-on system and you move to the edge-on system to the face-on system. So the result from this is that most of our Bulges span a wide range of angular momentum, for example, and also that most of them are in this region of the diagram, and therefore they are not isotropic. And this is because to be isotropic, you need to be on this line or in this side of the diagram, like these galaxies are. However, most of these galaxies can still be anisotropic, because if you think on this line going from here to there, it could be that it's just a projection effect, that these galaxies are here. It's just an inclination effect, and this galaxy could be perfectly on this part of the diagram. So most of our galaxies are compatible with being isotropic, anisotropic systems, so they need some anisotropic orbits in order to get the shape that we see in these Bulges. And a final conclusion that I put with an asterisk here, and when you see an asterisk, you should look at the small letter at the end of the contract, right? And the small letter in this case is this line over here. This is the line that was defined to separate fast rotators and slow rotators by the Atlas 3D team. So this means that galaxies or Bulges over this line should be fast rotators, and galaxies under this line should be slow rotators. But this line is completely empirical. So the difference of the red line with the other lines is that this can be derived from the virial theorem, but this one is completely empirical. And it has been defined for galaxies as a whole. And now we are using Bulges. So it is not clear how we can use this line to separate fast rotators and slow rotators in terms of Bulges, but I put it here just for comparison with other works. So this is what we obtained for our Bulges, and let me now compare this a bit with a sample of ellipticals and with our disk. So if we plot here the sample of elliptical that I showed you at the beginning, these are the red points. So you can see how many of the ellipticals are in this region. And this is normal because they were a bit shifted in mass, and you expect that galaxies with higher mass should be more slow rotators. The fraction of the slow rotators should increase when you move to higher stellar masses. But still, there are a lot of ellipticals that share the angular momentum, at least the position in this diagram with the Bulges. So they can be compatible with our Bulges. If we plot our disk, this is what we obtain. Of course, for the same galaxy, if you assume that the lambda is a constant rising profile, in the same way as, for example, the velocity rotation curve of a galaxy, you will expect that for the same galaxy, the measurement of the angular momentum in a larger aperture will result in a higher lambda. But the interesting thing is that there are some disks that can be compatible as well with the position of our Bulges on here. Remember that at the beginning I told you that I wanted to compare the photometric and the kinematic properties of the galaxies, right? So this is what I do here. And the idea here is to try to see if previous works that divided classical and pseudo Bulges or disk-like Bulges in terms of the photometry or kinematics are okay, or if we see the same things. So what I did here was exactly the same. This is the same plot, the lambda epsilon diagram. The points are in the same position as before. But in this time, I color-coded the points depending on one photometric property of the bulge. In this case, is the Sersic index. So red is higher Sersic index, blue is lower Sersic index. In this case, is the bulge to total ratio. So red is higher bulge to total, and blue is lower bulge to total. So if you think on the previous theories that I showed you at the beginning, you will expect that low Sersic index should be more disk-like, so they should rotate faster, and higher Sersic index should be more classical-like, and then rotate slower. But if you look at this, there is no clear correlation in this, right? So there is not real correlation of the color of the points with the position on the diagram. So this was quite puzzling at the beginning. And the first thing I saw is that this is an inclination effect. Remember that I told you at the beginning that these lines represent inclination. So maybe the position of these points in this diagram could be shifted just because of the different inclination of the galaxies, of the bulges, right? So in an ideal case, what you would like to have is a plane like this in which you plot the lambda, but in this case, the projected lambda, as a function of one of your properties. It could be the Sersic index in this case, but you can put here the bulge to total ratio, right? And this is more or less what you will expect in the sense of the projected lambda. And this is what we obtain. So the blue points are the same points as before, so it's not depth projected. And the underlying histogram that you see here is a statistical depth projection. For a given bulge, if you want to depth project the lambda, you need the three parameters. Remember, you need the inclination, the anisotropy, and the intrinsic shape. And we don't have access to the inclination, to the intrinsic shape or the anisotropy. But we can compute statistically what are the values of these two parameters that are compatible with the position of our points in that diagram. And then use all this to depth project the values of the lambda. And this is what is shown here in the underlying black histogram. So for each point, we have a range of possible values of the projected lambda. So, but of course, this is not what we expect from the common theories. If you look at this, you can see that you can think that this is a clear trend. If you then apply some statistical tests like the Spearman correlation coefficient, it's just about 0.5, 0.4. So it's not quite a strong correlation. Actually, if you remove these points, it's more like a blur of points over here. And we try to explain this in terms of our formation mechanism, right? So for example, yeah. The bulge. It's a bulge, yeah. These are bulge points, and this is bulge, yes. For example, if you need to populate this region over here, what you can have is to move, for example, these like bulges to this direction, something like this. Now think on the way we think that these like bulges are formed. So you have gas in the plane that is moved to the center through the bar, and then in the same plane, you start forming stars and create a pseudo bulge. So it's very difficult from this formation mechanism that you get something which is very puffed up in the vertical direction, in the sense that it's very difficult to get from a disk-like bulge to increase the, for this scenario of formation, to increase the Sersic index. So maybe this is not the best way to reproduce this diagram. So what happens if classical bulges can populate everything? So for example, if with mergers, we can populate the whole parameter space. And this is something that is now, many groups are starting to see now, is that you can create what we call disk-like bulges in terms of their observational properties with major mergers in cosmological simulations. So now we are reaching the point in cosmological simulation when we can resolve bulges, at least to some degree. And the properties that we are obtaining are quite puzzling. For example, this is a paper by Alison Brooks and Christensen. This is another review paper from this year. And here what they show, these are cosmological hydro simulation. What they show is this is the mass of the central part of the galaxy, that you can assume that this is a bulge. And this is the total virial mass of the galaxy. The empty symbols are the original galaxy, and the field symbols represent the galaxy after the mergers, right? So this is the trend that you will expect, for example. So when you have a merger, you will increase the total mass of the galaxy and also the central mass. This is what we expect in this kind of theories. But they are showing also that some galaxies, even very massive galaxies, can decrease the central mass. So it's not always that mergers increase or create a growth of the bulge, but you can also decrease the mass of the bulge. And in this case, this is mainly due to the new recipes for the feedback that you include in the simulations. This is another example of a cosmological simulation in which they directly create, of course with some initial conditions, but they create this like bulge with major mergers. And you can see how this is the Cerseic index as a function of the time, and they get that this low Cerseic index is maintained over the whole, at least over 4 gigayears of the time of the galaxy, even if you have mergers happening in this galaxy. So now it's not so clear that you can have from mergers only classical, like from the observational point of view, but mergers can also create low Cerseic index or bulges which are rotating. So what we think is that this relation or this kind of blur of point that we have in this plane can be explained by major mergers. And here, what I have done is just a test. This is a very preliminary plot in which I have used some simulation from the Gallmer set of simulation. These are cosmological simulations as well, of major and minor mergers. And I have analyzed these mergers in the same way as I have done for my galaxies. So I have decomposed the images of these galaxies. I have computed a Cerseic index. I have analyzed the stellar kinematics in the same way, creating velocity maps and analyzing the lambda. So since these are simulations, we can get the edge-on view quite nicely. And this is what is here shown with the red stars. So basically, this is a sample of about 90 galaxies that we have used from this simulation. And what you see is what I was telling you before. You get a complete mess around this plot. So probably we are now seeing that mergers are not creating only this kind of very massive elliptical-like bulges in the center of the galaxies, but mergers are also able to create what we call from the observational point of view disk-like bulges, but which from the formation scenario is not what we call disk-like bulges. So this is the end of my talk. So these are the conclusions. So I hope that I have conveyed the message that galaxy bulges are important for the study of galaxy formation. In our particular case of the lenticular, remember that our galaxies were high stellar masses, they were in the red sequence, and they were in the field. So our conclusions about the relation of the photometry and the stellar dynamic of the bulges, and our explanation that they should be formed at high redshift for major mergers, or at least with some dissipation through some dissipational processes, are also in good agreement with the global properties of the galaxy, because this is what you will expect for galaxies of this size. And with this, my last point is that I'm not saying, for example, that lenticular galaxies are only formed by major mergers. This is not what we are saying. For our particular sample of galaxies, which are very particular, as you see, and they are in the field, we think that major mergers are the main contributor to the formation of these galaxies. But still, if you look at galaxies in galaxy cluster, I think that most of these galaxies could be formed in the other way. Most of these lenticular galaxies could be formed by just stripping and transition from spirals into lenticulars. And that's all. Thank you.
Thank you, Jairo. Very nice and interesting talk. I have 2 comments and 1 question for you. First, the comment is that in the cosmological paradigm is not a problem, the lack of bulge. we have demonstrated in 2 papers that with the merger rate predicted in the lambda CDM, we produce a lot of galaxies that are bulgeless. And this is because the halo-halo merger is not the same than the galaxy-galaxy merger. You know, you can have a major merger because the ratio of the halo masses are larger than 0.25 or something like that, but the galaxies that are living in there are not proportional. The masses of them are not proportional to the halos.
And this happens for galaxies of 10 to the 10 solar masses?
Yeah, we demonstrated papers that we reproduce this bulge to total ratio versus the mass. At low masses, we have almost 30–40%. In fact, we have more than observed bulgeless galaxies. The problem is to the inverse, if any.
Because I know that for low mass galaxies, there are some groups that they have get into dwarf galaxies without bulges, but using more feedback from supernova.
No, it's not.
Kind of
Our approach
so
was semi-empirical, let's say, just taking the merger rates from the simulations and using the observations of the baryonic mass to halo mass ratios, also inferred from observations, and we have shown that are using the recipes from Hopkins for forming the bulge, yeah?
Okay.
So there is no such a problem.
Okay.
And the second interesting question that I think is in agreement with your results is that bulges are composite.
Yes.
In our scheme, we are able to predict, to show how is the bulge to total ratio and the properties of the bulge at each redshift. And we show that sometimes after the mergers, the bulges are classic. But then this can grow again, and we can have a pseudo bulge formed by secular processes, bar destruction, these kind of things. So at the end today, we predict that, for example, massive galaxies are dominated by classical. Most of the stars in this bulge came from mergers, and the mergers typically give you a Cercic index of 4, a classical bulge. But as you go to galaxies less massive than 10 to the 11, you have half-half, and the smaller galaxies are completely dominated by the secular bulge. Yeah. So I think your results are for S0 galaxies that you have composite bulge, bulges that can be some fraction formed by classical as a classical bulge, some fraction formed as a by secular processes, a pseudo bulge. So my question is, could you suggest some observational test for this question, the composite bulge?
Actually, I have a paper in 2014 in which what we did is to study a sample of bar galaxies, and we did it with the VLT data using high spectral resolution. It was long slit, okay? So what we did was to put the long slit in the center of the galaxy, and what we saw is that for our sample was about 10 or 11 galaxies, and 80% of the galaxy show a composite bulge, in the sense that you will have a big bulge in the outer part. Well, there were different combinations of them, depending on if there were something that I didn't introduce here is the boxy peanut bulge as well. So what we found is that at least 80% of our barred galaxies were composite, in the sense that they have both a classical and a pseudo coexisting in the same galaxy. So this goes in your direction. Related to this, the problem that we had with this is the spatial resolution of CALIFA, in the sense that it's not enough to resolve the very central parts. But we have new data that we are now analyzing, in which we have a better spatial resolution in the galaxy center. So it's a smaller field of view, but with higher resolution, spatial resolution. And what we aim now to see if there are two different components also in the galaxy center. This is something that with the photometry you cannot see. Even if you go to the very, very detail, you cannot see in the photometry that there are two bulges. But from the stellar population and from the dynamics, if you see some disk rotating very fast in the center of the galaxy, you can try to do this. And this is something that we're exploring now. And it could be also some reason why we have this spread on the properties of the bulges in the lambda versus Cercic, for example, plane. Yes. Yeah.
A very nice talk, Jairo. I have a couple of questions. What is the fraction of barred galaxies that you have among your S0 sample?
This is another point. I forgot to mention this for your question.
Yes.
It's about 80%.
8%.
80%.
80%.
So
okay. So
it's quite a lot. And this is something also that is very puzzling, and was very puzzling at the beginning, because you will expect that if you have a lot of bars, you will have a lot of pseudo-bulges in the center. But our explanation for this, and this is completely a hypothesis put there, is that maybe at the time that the bar forms, you don't have already many gas in the disk. So you don't have the gas to be fed into the center of the galaxy and produce a new pseudo-bulge. So the only possibility that we have is that the galaxies were already red at the time that the bar forms, and then you don't have this gas that can fall into the center and form a new component. And
because I am thinking, if you discard the merger process and you think that the ramp pressure stripping could be a possibility for losing the gas, the bar, well, the arms and the gas. So if they are isolated, can you think in a process that keeps you the spin or the velocity, the rotation of your objects? I don't think it will be affected by the ramp stripping.
No, the stellar angular momentum is not going to be affected.
You will be keeping the rotation you have since the beginning.
Yeah. This
and you don't think need mergers. That's my own.
Yeah, this is what we did in the paper with Miguel Querejeta, the paper that I mentioned in the introduction as well. It's exactly this. What we did is to plot the angular momentum versus concentration for a sample of lenticular galaxies, but also for late-type spirals. And what we saw is that the late-type spiral had a different position on this angular momentum versus concentration plane. And if you assume that if you affect the gas, I mean, for random pressure stripping or whatever, you are not changing the angular momentum of the stars, then you cannot reconcile these two things. So you cannot move just the spirals into the position of the lenticulars using some gas process. So that's why we think in this paper also, the conclusion was also that probably mergers were playing a role on the formation of these lenticulars, which are more or less our conclusions here.
Any other question?
Of course. Well,
so the lambda parameter is not really useful.
Well, we can discuss this. We can discuss this with Sebastian. Yeah. He has different ideas.
We have some funny ideas about that.
But it's not just the lambda. I mean, what I'm trying to show here is that this idea that we have in mind that we can separate classical and pseudo-bulges based on the observational properties is probably not true, because they are completely mixed, or you have different processes forming different kind of bulges. So it's not the right way to approach. So you should define classical or pseudo depending on the formation mechanism and not on the observational properties. Because if we continue in this line, we are messing up everything. This is the final idea of.
Just a note, when you mention about the origin may be mergers, I think you should remark that they're early mergers.
Yeah, high redshift.
Yeah, because the people, every time the people say merger, people think in the mergers actually happening. Yeah, these mergers that you may don't see the evidence of that mergers anymore.
No, you need for the mergers, you need the time enough for the merger to happen, and then to create a disk around the remnant, and then to fade, and then you need some time. So these mergers has to be a high redshift. The one interesting thing is that they have to be gas rich. If you have a gas poor merger, you don't get with a lenticular galaxy.
So it's beyond 10 gigayears or something like that.
Well, this is, I don't know, more than redshift, I don't know, 2 or 3 probably. Yeah.
¿Alguna última pregunta? Agradecemos a Jairo otra vez.